We tested hypotheses for two means. Now we're going to construct and interpret the confidence interval regarding the difference of two independent means. In order to construct a 1 minus alpha times 100% confidence interval for the difference of two means, let's say that we have a simple random sample of size n1 is taken from a population with unknown mean mu1 and unknown standard deviation sigma 1. Also, a simple random sample of size n2 is taken from a population with unknown mean mu2 and unknown standard deviation sigma 2. If the two populations are normally distributed or the sample size are sufficiently large, that is, each one of them is bigger than 30, a 1 minus alpha times 100% confidence interval about mu1 minus mu2 is given by the lower bound is equal to x1 bar minus x2 bar minus t sub alpha divided by 2, the critical value, times the margin of error, which is square root of s1 squared divided by n1 plus s2 squared divided by n2. The upper value is similar to the lower bound. We just change the negative sign to a plus sign. T sub alpha divided by 2 is computed using the smallest of n1 minus 1 or n2 minus 2, just like we did previously. Let's construct a confidence interval, a 95% confidence interval about the difference between the population mean weight of a state quarter versus the population mean weight of a traditional quarter. This is an example from a previous video. Go back to the video to review that example. We have already verified that the populations are approximately normally distributed with no outliers. Recall that we computed x1 bar, which is 5.702, and the standard deviation, the sample standard deviation from the state quarters, 0.0497, and x2 bar for the traditional quarters, and the standard deviation for the traditional quarters. So we have the standard deviation for each of these samples, and we have the mean of each of these samples. And then we computed the t sub alpha divided by 2, which is basically we have alpha is 5%, so t sub alpha is 0.025, which is equal to, you can compute it using the t dot inverse dot 2t of alpha comma n minus 1. This is the smallest of degrees of freedom. You're going to get the number 2.131. So this is how you're going to compute the t critical. You can use the tables or you can use Excel. I used Excel to compute that value. Now, to construct the confidence interval, you're going to compute the lower bound. Again, the lower bound is x1 bar minus x2 bar minus the t sub alpha divided by 2 times the square root of s1 squared divided by n1. So this is s1 squared and this is n1. And this is s2 squared and this is n2. You're going to get this number, which is, I believe, is not accurate. The accurate number is 0.0096. And then the upper bound is similar, but we changed this sign from negative to positive, so you're going to obtain this other number. So the conclusion for this, we are 95% confident that the mean weight of state quarter is between 0.008696 and 0.0974 ounces, more than the mean weight of the traditional quarters. Since the confidence interval does not contain 0, we conclude that the state quarters weight more than the traditional quarters. If we have 0 in the interval, we're going to say we can't conclude that the state quarters are way more than the traditional quarters because 0 is in there. When the population variances are assumed to be equal, the pooled T statistic can be used to test for the difference in means for two independent samples. The pooled T statistic is computed by finding the weighted average of the sample variance and uses this average in the computation of the test statistic. The advantage of this test statistic is that it exactly follows the student T distribution with n1 plus n2 minus 2 degrees of freedom. The disadvantage of this test statistic is that it requires the population variances to be equal. We would use the pooled two-sample t-test when the two samples come from populations that have the same variance. Pooling refers to finding a weighted average of the two sample variances from the independent samples. It is difficult to verify the two population variances might be equal based on sample data. So we will always be using Welch's T when comparing two means.